Hello, and welcome to today's lesson looking at the phenomena of resonance. So in today's lesson, what we're going to be doing is we're going to be looking at describing what the concept of resonance is. So we're going to, for successfully learning today's lesson, define what resonance is, look at the effect of resonance in the real world, and describe the benefits and the disadvantages of resonance occurring in different materials, which falls into the following part of the AQA A-Level Physics specification: forced vibrations and resonance, which is found in the periodic motion section of the course. So previously we've looked at the idea of an oscillating system. Now we can review these ideas by considering a slinky. Now a slinky can act as an oscillator in the correct situation. A slinky will oscillate back and forth over its equilibrium position, and we can make it either a forced oscillator or a free oscillator. So a slinky can be actually either type of oscillator. So we can look at this in the following situations. So if we look at this system where we make the slinky act as a forced oscillator, the driver provides a driving force to the driven oscillator. So the driver, in this case my hand, provides energy into the driven oscillator, the slinky, to change the frequency. So work is done by a driver into the driven oscillator. So if I hold one end of a slinky and let the other oscillate freely, we actually have the slinky operating as a free vibrator. So at what frequency will it actually operate at? So in this particular situation, because the slinky is acting as a free vibrator, the slinky is vibrating at its natural frequency. But now, if I move my hand up and down, I force the slinky to vibrate. So at this particular point, now I'm acting as a driving force in the situation. The slinky is carrying out forced oscillations because there's a periodic driving force acting upon it, so it's vibrating at its driven frequency. So if the driving frequency is now lower than the natural frequency, what happens inside the amplitude of the oscillation? So in this particular situation, it's clear to see that when the driving frequency of a forced oscillator is lower than the natural frequency, the amplitude of oscillation is lower for the system than its natural frequency. However, if the driving frequency is higher than the natural frequency, what do you know about the size of the amplitude of oscillation? Well, when the driving frequency of the forced oscillator is higher than the natural frequency, well, the amplitude of oscillation is higher for the system than the natural frequency. But more importantly, let's look at the following situation. If the driving frequency is the same as the natural frequency, what is the size of the amplitude of oscillation? Well, in this particular example, you can see the following. Now, when the driving frequency of a forced oscillator is the same as the natural frequency, the amplitude increases massively, maybe even exponentially. Now, we call this effect resonance. So, when a system acts as a free oscillator, it oscillates with the natural frequency, f0. If that system, when it's acting as a forced oscillator, has a driving frequency the same as the natural frequency, then the amplitude becomes very large. This effect is called resonance. So this graph shows us the amplitude of a simple harmonic oscillator, when it's vibrating against the driving force applied to it. Now, resonance can only act on a forced oscillator. A free oscillator cannot undergo resonance. So resonance occurs when the driving frequency equals the natural frequency. Now, we can observe resonance as a massive increase in amplitude of the oscillating system, because resonance leads to a large increase of energy into the system. So here, for example, is resonance occurring in glass. There's a periodic driving force acting on the object causing this resonance. Here's another example of resonance occurring in glass. So a periodic driving force is acting on the object, causing it to resonate. Again, here's another example of resonance occurring in a helicopter, where the periodic driving force is acting on the object, causing a resonance, which leads the energy store of the object to increase dramatically. So here's a simplified version of the resonance graph. You can identify the resonance frequency from identifying the frequency with the highest amplitude, and they can link it into the idea of energy stores, because the amplitude links into the amount of energy stored in that particular object. High amplitude, high energy store. low amplitude, low energy store. So we can identify the resonance frequency because it's the frequency with the highest amplitude, which is also the natural frequency of the system, because the resonance frequency must equal the natural frequency of the system. So to determine the resonance or natural frequency of a system, you've got to take many experimental points around the peak of the graph, which is a very important idea. So you must decrease the interval around the peak values. So for any oscillator, the effective resonance happens when the natural frequency equals the driving frequency. This causes the amplitude of the oscillator to increase massively, and this happens because at the natural frequency, that's when the system's at its most stable. This means the system can absorb energy from the driving force easily. This increases the amplitude. So pushing a person in a swing is a common example of resonance. The loaded swing, which is just a pendulum, has a natural frequency of oscillation, its resonance frequency, and resists being pushed at a faster or slower rate. Now, resonance can only be observed in forced vibrations, as the driving force is where the oscillator absorbs the increased energy from. However, we've only assumed that the oscillating system is undamped. It has no damping force acting upon it. But in most situations, a system, an oscillator, has a damping force acting upon it. Now, resonance can only really occur when dampening is small, because dampening makes the simple harmonic system energy move into the internal energy store of the surroundings. So dampening lessens the effect of resonance. Now, dampening reduces the size of oscillations at resonance. It reduces the amplitude. There's still a maximum amplitude reached, but it's much lower than when the system is undamped. We say that dampening reduces the sharpness of resonance, because so if you want to lessen the effect of resonance on your system, either change the natural frequency of the material to change the resonant frequency, or include dampeners to provide a dampening force. So dampening makes the simple harmonic energy in the system move to the internal energy of the surroundings. It lessens the effect of resonance. So the stronger the dampening, the smaller the effect of resonance. So we say dampening reduces the sharpness of resonance. What this means in essence is that the dampening lessens the effect of the resonance spike in amplitude. So heavily damped systems have a flatter response to an increase in driven frequency. So the heavily damped systems do not increase their amplitude very much near the natural frequency. So they are not as sensitive to the driving frequency as undamped systems. So they will have a resonant frequency slightly lower than the natural frequency, which you can observe in this particular graph. You'll notice that whilst the graph is have a smaller peak, it's flattened out, and the actual peak is slightly to the left than what it was when it's undamped. The three major effects of dampening on a system. So dampening lessens the effect of the resonance spike in amplitude, because the dampening forces causes the energy stored in the system due to resonance to be dissipated to the internal energy store of the surroundings. So the lighter the dampening, the larger the maximum amplitude becomes at resonance. The closer the resonance frequency is to the natural frequency of the system, and when dampening is lighter, the resonance curve is much sharper. So every oscillator system can undergo resonance, and we observe this effect in many everyday situations. So in this particular situation, the ball which moves with the most must undergo resonance, as it has the greatest energy store and thus the greatest amplitude of oscillation. So to undergo resonance, the natural frequency of the pole must equal the driving frequency produced by the man. Another example is a washing machine. So the motor of the machine drives the vibrations in the machine, which are at its natural frequency on one of the washing machine panels, which is why a washing machine is very noisy during one part of the cycle, because the motor is spinning at a particular frequency. So at some point of the cycle, the driving frequency of the motor equals the natural frequency of the metal which makes up the washing machine. This causes the panel to vibrate with an increased amplitude. It's at resonance, making a loud noise. It can even cause the washing machine to move slightly, but during the rest of the washing cycle, the motor rotates at a frequency which doesn't match the natural frequency of any part of the machine, and so there's no resonance occurring, so the machine's a lock. quieter. Another example is when you've got the idea of glass. So what can happen is if you cause a resonance of glass, so you have a driving force which is the same as the natural frequency of the glass, well therefore it will increase the amplitude that the glass oscillates at and can cause the glass to smash. Now a very famous example of a driving force on glass can be the human voice. So this can cause the glass to resonate, produce a large amplitude in the glass due to having a large amount of energy stored, and will cause the glass to smash. So actually the human voice can actually smash glass. Now a system can be made to oscillate with the driving force, so it's a driven oscillator. Now when the driving force begins to oscillate the driven object, the phase difference between the driving oscillation and the oscillating object is zero. The driver and the driven are in phase. So at the start of this process, the driving oscillator, which is the signal generator, and the spring, the oscillating object, are oscillating in phase. But if the system has its driving frequency increased, as it goes up to its natural frequency, it will absorb more and more energy, causing the amplitude of oscillations to increase. But when the driving frequency equals a natural frequency, you achieve resonance, and resonance is only achieved when the phase difference between the driver and the driven object is pi over 2 radians, or 1/4 of a wave. So when a driven oscillator is oscillating, such as the spring, it's going to be pi over 2 radians behind the signal generator, the driven. So therefore the signal generator is leading the spring into oscillating because the signal generator is providing energy into the oscillating system. So at this point the periodic driving force is then exactly in phase with the velocity of the oscillating system, which is causing this increase in amplitude, which is why we observe resonance, which is why it has to be pi over 2 radians ahead of the object it's driving. Now, eventually, if we increase the driven frequency higher and higher above the natural frequency, well then the driver is now pi radians, half a wave ahead of the driven. So in this example, the signal generator is pi radians ahead of the spring. So this again has to be ahead of it because the signal generator is leading the spring into oscillations. The signal generator is providing energy into the spring to oscillate, so it's got to be ahead. So we can summarize the phase difference between the driver, which is the thing which is providing the force, and the driven, the thing which is oscillating, in a forced oscillator with the following. So before resonance, the phase difference between the driver and the driven is 0 pi radians. The driver and the driven are oscillating with the same cycles, they're in phase. At resonance, the phase difference between the driver and the driven is pi over 2 radians. The driver is 1/4 of a cycle ahead of the driven. After resonance, the phase difference between the driver and the driven is pi radians. The driver is half a cycle ahead of the driven. So let's just summarize the properties of forced vibrations as the following. So we'll look at the situation when you increased your applied frequency to a driven oscillator, such as a spring or a slinky. So when the driven frequency is below the natural frequency and you increase the applied frequency, the amplitude increases. When the driven frequency is the same as the natural frequency, the amplitude is a maximum, it's at resonance. And then when the driven frequency is above the natural frequency, the amplitude starts to decrease again. Now, let's look at the phase difference. When the driven frequency is below the natural frequency, the phase difference starts at 0 and then begins to increase when the applied frequency increases. When the driven frequency is the same as the natural frequency, when you're at resonance, the phase difference is pi radians, and then when the driven frequency is above the natural frequency, well, the phase difference starts at half pi radians and increases to pi radians as you increase your driven frequency. So we can actually show this concept of resonance with a number of different examples, but a simple setup is one of several pendulums. So the heavy swinging ball acts through the suspension wire to drive all the other pendulums to act at its natural frequency. Now, only the pendulum with the same natural frequency vibrates with a large amplitude, as this is the pendulum that's resonating. This pendulum has the same length of wire as the driving pendulum, but the other pendulums show little movement because the driving frequency of the driven pendulum doesn't match their natural frequency. Now this setup is called Barton's pendulum. So here's a diagram of Barton's pendulum. In this situation, pendulum X acts as the driving frequency. It's the driving pendulum. And as this is providing the driving force, okay, therefore it'll be pi over 2 ahead of the pendulum it's making vibrate when it's at resonance, and only the pendulum with the same string length will have the same natural frequency as the driving frequency and therefore will only resonate. And why do you know it has to have the same string length? Because the string length and the strength of gravity the pendulum are in are the only two factors that can affect the time period and frequency of the system. So this means the pendulum, which has the same string length as the driving pendulum, will vibrate with the resonance frequency. And this will be observed when the pendulum oscillates in a higher amplitude than the other pendula. So, for example, in this situation, you would look across and you notice that pendulum D has the same string length as pendulum X. So what you would observe is pendulum D would oscillate at a much higher amplitude than the other pendula because that pendulum is oscillating at resonance because it's the driving frequency from pendulum X matches the natural frequency of pendulum D. So here, for example, is a set of Barton's pendulum set up live and in action. So that's the driving pendulum. That driving pendulum provides the driving force to move the other pendula. So the different driven pendula are moving by the driver pendulum. So let's think about it. Which pendulum will oscillate in resonance and why? And how far behind will the driven pendulum be? And what is the reason for this? So pendulum B will oscillate in resonance as it has the same natural frequency as the driven frequency. That's because it has the same frequency as the driving pendulum as they have the same length of string, which is what affects the frequency and time period of the pendulum. Now the driving pendulum will oscillate pi over 2 radians ahead of pendulum B when it drives it as it leads the pendulum, giving it energy. Now, resonance can also have some devastating effects too. So in 1940, resonance caused a bridge in Tacoma, Washington in the United States to collapse. The design of the bridge led to resonance as wind turbines generated a driving frequency that matched the natural frequency of the materials of the bridge at a relatively low wind speed. Now, any bridge can oscillate because of its spring constant and its mass. So here's an image of the Tacoma Heights Bridge swaying under resonance. So for the first 4 months it was open, it was actually nicknamed Galloping Gertie due to its tendency to have large oscillations. But on November the 7th, 1940, the crosswind patterns hit a resonance frequency such that after several hours of twisting with an amplitude of several meters, the concrete of the bridge deck failed and most of the bridge fell into the Tacoma Narrows channel, which is what it looked like in this particular situation. So what was going on is the natural frequency of the materials matched the driving frequency of the bridge due to the wind. That led to resonance occurring. So the energy stored of the system increased dramatically and the amplitude of the bridge increased very, very high, which eventually led to the bridge collapsing with so much stress the actual structure was under, so it led to the bridge ultimately collapsing into the Tacoma Narrows channel. So you can see here, ever since that point, bridges have been modelled in wind tunnels, so engineers have to work out the natural frequency of the metals used and ensure the winds in that region don't vibrate the metals to that same frequency. Now there's a more modern example of bridge resonance in addition to the Tacoma Heights Bridge, and that to celebrate the year 2000, a pedestrian bridge was built across the Thames in London and it opened on June the 10th in the year 2000, and it was estimated that between 80,000 and 100,000 people crossed the bridge on the opening day, and at its busiest at one single time there was 2,000 people on the bridge. Now according to engineers, at this point unexpected movements occurred because different parts of the bridge suffered excessive sideways wobbling, and actually pedestrians struggled to continue walking and had to hold onto the rails, and some were actually reported to be seasick. Now there was no problems with the vertical movements, but the bridge had lateral and twisting modes of vibrations, and these had a resonance at several different frequencies just below 1.5 Hz. Now the normal walking pace of a human is between 1.6 Hz and 2.4 Hz, but sightseers were moving more slowly when they were going across the bridge. And then the big problem was once the bridge started to oscillate in resonance, the people actually started to walk in step with the swings. This meant that the driving frequency of the people walking across the bridge matched the natural frequency of the bridge. And so what this meant is the bridge underwent resonance. So in investigations, experiments were carried out in which large crowds of people walked up and down the deck of the bridge in various ways and at various speeds, and it was actually found that only 166 people were needed in a part of a bridge to have a serious effect of resonance. And so the analysis of the data determined that it was only under certain conditions that resonance would occur, but engineers had to think about what they would do. Now, one option would be to make the bridge stiffer, so the oscillations would naturally have a smaller amplitude for the forces involved, but this is very difficult to carry out and very expensive to install, so the decision was taken to add something called dampeners, which are quite like shock absorbers in various places throughout the structure. So this meant that the oscillations produced by the resonance were dulled by the effect of dampening. The dampeners had exerted a dampening force which dulled the actual peak of the resonance and flattened out that curve. This meant the energy stored in the system could not increase as dramatically, and this is why actually dampening can be a very useful effect in the real world. So placing dampeners on certain structures can dull the effect of resonance and reduce its sharpness, which is very, very useful in certain situations. So what have we learned in today's lesson? Hopefully we understand what the effect of resonance is and the effect of dampening on the sharpness of resonance. And if we can define what resonance is, we've learned in today's lesson, we can look at the effect of resonance in the real world, and we can describe the benefits and the disadvantages of resonance occurring. I hope you've enjoyed this lesson looking at resonance and how dampening can affect resonance in the real world and the different situations where we've observed resonance occurring. Thank you very much for listening to today's lesson and have a lovely day.